Okay, welcome back. So let's practice using the same problem statement from the last question for using the psychrometric chart and specifically looking at specific questions that we are asked. Here we want to find the mass flow rate. Here we want to find the total cooling provided. So let's do these questions real quick, FE type questions. So it's the same as last time. We have 5,000 pounds cubic feet per minute of outdoor air brought into an HVAC system, and with an outdoor intake size of 2 by 3 feet. The air is at 95 degrees Fahrenheit and 40% relative humidity and is cooled down to 55 degrees Fahrenheit and 80% relative humidity. The mass flow rate of the air being conditioned is most nearly what? So again, we have an air conditioning. The air comes in at a temperature of 95 degrees Fahrenheit, which is stated here, and 40% relative humidity. Then this air comes out from our HVAC system here. It comes out at a temperature of what? The 55 degrees Fahrenheit, and omega, the relative humidity in this case, is 80%. So what we want to find here is the mass flow rate of the air being conditioned. The air being conditioned is this air, right? The air comes in here. This is the air being conditioned. What is the mass flow rate of this air? And we know this is going to be our m dot. It's a flow rate. It's a rate. That's why we have an m dot. And let's call it sub A, for the dry air. So the way we can determine that is by using the following equation. We know by definition the mass flow rate, in this case of the dry air, is going to be the volume of the flow rate, which is essentially just of the flow rate, which is given to be the 5,000, right, cubic feet per minute, divided by the specific volume. So specific volume, I'll just write it here, specific volume, which is the letter is our V, right? The lowercase v. So we know this top, we know the top, we know it's 5,000 cubic feet per minute. The specific volume here, so I figure out that M, specific volume is going to be arrived at from the psychrometric chart. So let's find that real quick, and we're finding it again at these conditions, at 95 degrees Fahrenheit and 40% relative humidity. This is what we want to find, the mass flow rate of air being conditioned. So let's go to the chart, and we can go to Thermodynamics, and it's going to be on page 175, I believe, just like the last example. So we're on page 175 in the new FE Handbook 10.0. So we're going to plot what temperature? We're at 95 degrees Fahrenheit and 40% because we want to look at the mass flow rate of the air being conditioned, the air coming in. So what do we do here? We go to 95, which is already plotted from the last example. This is going to be the dry bulb temperature. You go to 95, go all the way up until we intersect the relative humidity of 40%. So we go until we intersect it at this point. Then the way we can determine our specific volume, which is the value we need, is by looking at these lines here. These lines going up at an angle. So we know this is going to be 14 cubic feet per pound. Cubic feet per pound of dry air. This line is 14. This line is 14.1. This line is 14.2. This line is 14.3. That means since we're at this point, we have a specific volume of 14.3. So let's write that down. The specific volume at these conditions of the air coming in is going to be 14.3. That goes on the bottom, right? 14.3, and it's going to be cubic foot per pound. So that's that. And the volume of the flow rate is just 5,000. That's given. 5,000 cubic feet per minute. So the cubic feet units cancel. We should get our mass flow rate of the air being conditioned. It's going to be around, I got 349 38.65. And that has units of pound per minute. So that's that. We have the right units, and it's going to be around A. So that's our closest answer. So that's A. So that's the first portion. For the second portion of this question, we want to find, it's the same statement, but the difference here, we want to find the total cooling provided to this airflow in kilowatt of cooling. Is most nearly what? We want to find the total cooling provided in kilowatts, units of kilowatts. So the total cooling provided would be simply our Q. It's going to be our Q value for the cooling provided. We take the mass flow rate of the air times the change in enthalpy. So let's call it Q sub L for the cooling. And it's going to be the mass flow rate of air, which is, we already have that, right? Times our H1 minus our H2, which is the change in enthalpy. So the change in enthalpy, we've already determined that, and we already have the mass flow rate. The change in enthalpy, if you refer to the last question, the last video on the psychrometric chart, we found the change in enthalpy by looking, we know this was our H1 value here, and I believe we got around 38.8, and for the H2 value, we plotted 55 degrees Fahrenheit. We went to the 80% relative humidity line. We intersected here, and we went across and intersected at this point. And for this, our H2 value was around 21.3. So let's write those down. We go back. So it's going to be the mass flow rate, which is what we determined here, 349.65 pound per minute, times our H1 was around 38.8 BTU per pound, minus our H2, which is 21.3 BTU per pound. So now you can do the math here, and we get our Q sub L will be, I got around, do the math for this. So I did not do the math yet for this one. So it's 349.65 times 38.8 minus 21.3. So it's around 6,118.88. And this will have units of BTU per minute. So this has pounds. These pound units cancel. So we're left with BTU per minute. But remember here, we want our final answer in kilowatt of cooling. So we have to go from BTU per minute to kilowatt of cooling. How can we do that? Remember, you have your conversion tables in the FE handbook. Knowing how to use these will be very crucial. So let's go back to the conversion tables. And let me go down here. So let's look here. The way I do this is just type BTU. We know we're going from BTU. This is BTU to joules. No, not good. This is BTU per hour to kilowatt. Okay. So that would make sense, right? So what we have to do here is convert the BTU per minute, which is what we got from our answer here, to BTU per hour. Then we can go from BTU per hour to what? To kilowatts. By what? By dividing by 3,413. We multiply to go this way to obtain. So we have to go backwards in this case to go from BTU per hour to kilowatts. So let's do that. Let's go back. The first step again is to convert this BTU per minute to BTU per hour. And we know there's gonna be the 60 minutes in 1 hour, right? So we take this, multiply it by the 60 minutes in 1 hour. The minutes cancel. We get our new value in BTU per hour. So I'm going to take this and multiply it by 60. It's around 367,132.5 BTU per hour. Now to convert to kilowatts, we're going to take this value and divide it by what? we divide it by the 3,413. From BTU per hour to get to kilowatt, we divide by 3,413. So we divide by 3,413. So we take this whole value and divide by 3,413, and we get our answer in kilowatts. And if you do the math, you should get around 107.57 kilowatts. So this would be our answer here. And I noticed there is no answer choices, so all of these are wrong. I wrote this question incorrectly. So this is the correct answer, and it should be, again, 107.57 kilowatts. Sorry about the answer choices. Next time I will double check that. And I hope that helps. Let me know if you have questions. Thank you.